Good morning everyone. We are Group Trifinity and we are here to present our project titled Edge Computing for Real-Time Circuit. My name is Jayalakshmi. Along with me are my teammates Rabiatul and Ayman. In this project, we explore how edge computing can be applied to electric circuits to enable real-time monitoring and faster decision making. We will be discussing our design process and the technologies we use like MATLAB, Simulink and Arduino, and how our system simulates a smart and a responsive circuit setup. Let's begin with a brief overview of the project and its objective. So this project explores how edge computing can enhance the performance of real-time electric circuits. By processing data locally close to the circuit, we aim to reduce latency and enable faster decision making in systems such as IoT, automation, and smart control applications. The main objective of our project is to design, simulate, and evaluate a system that connects electric circuit with an edge computing network. More specifically, we aim to monitor circuit behavior using sensors and microcontrollers to transmit real-time data through edge-based systems instead of relying on cloud processing. Also, we use tools such as MATLAB, Simulink, and Arduino to implement and test the setup. This objective helps us explore how edge computing can make electronic systems smarter and more responsive. To understand our project better, let's look at the background. First, we explored basic electric circuit components including Ohm's law, Kirchhoff law, and RLC circuit. These principles help us design a circuit that mimics a real-world sensing environment. Next, we studied networking protocols such as TCP, IP, MQTT, and UDP. These are commonly used to transmit data over the internet, but we focused on how to use them in edge computing to reduce reliance on central cloud service. Finally, we reviewed tools and technologies like MATLAB, Simulink, and Arduino, which allowed us to simulate the system and test it using actual hardware. With the context in the mind, let's now move on to the system design of our project. Over to Ayman.
Hi, my name is Nur Iman. The presentation with the system design and implementation. Okay. First, we design a series RLC circuit using Simulink. It includes a resistor, inductor, and capacitor in series, meaning the same current flows through all components. We use typical values, which is R equal to 50 ohms, L equal to 100 millihenries, and C equal to 10 microfarads. The key behavior we study is resonance. This happens when the inductive and capacitive reactance cancel each other. At that point, the circuit reaches minimum impedance and draws maximum current. This occurs at the resonant frequency FO equal to 1 over 2 pi times square root LC. Next, we added a networking system to monitor the circuit in real time. We use sensors to measure voltage and current connected to an Arduino for edge processing. The Arduino calculates values like RMS, then sends the data using the MQTT protocol, which is light and fast. The data is sent to the cloud, where we can store and visualize the results on dashboard. Okay. Then here is the full system flow. The circuit connects to sensors, then to the Arduino Edge node through MQTT to the cloud dashboard. Next is the implementation. In this step, we created the series RLC circuit in Simulink using components from the Simscape electrical library. The key parts include a DC voltage source as input, a series RLC branch, and measurement blocks to monitor voltage and current. We use a product block to calculate the power by multiplying voltage, and current. The scope and display blocks help us visualize the waveform and power output. We use typical values which are R equal to 50 ohms, L equal to 100 millihenries, and C equal to 10 microfarads, and a 1000 volt DC source. The power GUI block was added to run the time domain simulation properly. Here's how we implemented the simulation. First, we launched Simulink from MATLAB and created a blank model. Then we added all the required components: the voltage source, RLC branch, measurement blocks, scope, display, product, and power GUI. We connected the blocks. We connected the blocks to form a series RLC configuration where the voltage and current measurements fed into the product and scope blocks. After setting components value, we ran the simulation. We observe real-time voltage, current, and power waveform in the scope and the power values in the display. We also tested variance by changing component values to simulate RL, RC, or R-only circuits, which help us study both transient and steady-state responses. To simulate edge computing, we process data locally in Simulink. The product block's power calculation represents a form of local edge processing happening before data is transferred. We then exported the voltage, current, and power data into MATLAB or CSV files. Using MATLAB's MQTT toolbox, we publish the process data to an MQTT broker, which simulating real-time edge-to-cloud communication. This shows how data can be summarized and transmitted efficiently, just like in IoT system. To summarize, we built a complete simulation of a series RLC circuit with real-time power monitoring using Simulink. We apply edge computing ideas by processing data locally and transmitting results via MQTT. And finally, the setup can be extended to include real hardware like an Arduino for actual sensing and data publishing. This combination of simulation and edge computing makes the system more responsive and efficient for real-time circuit analysis. That's all from me. Thank you.
Hi and Assalamualaikum. My name is Siti Norbetaravia binti Amarizam. So, so I'm going to discuss about the part result analysis. So this is the result that we get from the implementation project while using Simulink and also MATLAB. So this is the column for parameter and also value. So the value for peak voltage is around 8.20 volt, and then for peak time is 0.0023 seconds. And then for latency H, minus 5 milliseconds. And lastly, latency for cloud is minus 150 milliseconds. So from this result, the voltage across the capacitor rise quickly following the step input by peaking at around 8.20 volt at 0.0023 seconds. It also indicates the predator transient behavior. So next, for the analysis part, so first, local edge processing significantly lower data transmission latency by up to 30 times compared to cloud-only processing. And then next, the bandwidth is saved by delivering just critical measurements rather than continuous raw data streams. And lastly, it also demonstrates the benefits of edge computing for real-time circuit monitoring. So for next part, I'm going to discuss about this the discussion part. So first, it effectively demonstrates the potential of edge computing in real-time analysis with MATLAB and also Simulink. And then it shows a significant reduction in data transmission latency, which is almost 30 times lower than cloud-only processing. And then it showed the effectiveness of edge computing in reducing delays. And lastly, I also demonstrate that edge computing reduce bandwidth consumption by providing just critical measurements rather than continuous raw data. So we also face some challenges during our implementation for the project, which is while replicating the edge environment and incorporating MQTT communication. So for this, the issue was successfully solved with MATLAB's toolboxes by demonstrating the software adaptability in addressing such complication. And then the Simulink model precise prediction of transient circuit behavior is proven by theoretical calculations and demonstrated the model's dependability. So not only challenges that we face, there's also some limitation, which is during project implementation, the each device was simulated rather than be physically implemented. And then the communication model also was simplified. So this simplification may not accurately reflect the complexities of real-world installation. So for for future work, we also best to recommend building the project by expanding it to multi-sensor networks by deploying the system on the hardware and also incorporating advances detection algorithms. So such advancements also would help to verify the use of edge computing in real-world electrical system monitoring and also may reveal new insight for improving system performance and reliability.
For the conclusion, okay, to summarize, this project successfully simulated a series RLC circuit using Simulink, allowing us to analyze both transient and steady-state behavior. We integrated edge computing by performing local power analysis within the simulation and used the MQTT protocol to transmit only the essential data. This approach helped us reduce latency and bandwidth usage, which are common issues in cloud-only systems. Although this work is simulation-based, it sets the stage for real-time hardware integration using devices like Arduino. This combination of simulation and edge processing supports the development of smart IoT systems, making circuit monitoring more efficient and scalable. That's all from us. Thank you.